Okay, so basically at this point we need to make some decisions about what we're going to do from here, like what we want this game to look like. I guess, let's see, maybe I'll just make these like super rare for now, so yeah, just so they don't distract us. So now they should fire, what, every 2,000 frames? That's not very often. That's like, what is that, like 3 times per minute or something like that? Yeah. Anyway, okay, so basically what we want to do from here is sort of get an idea of like what we want the game to look like. Yeah, no, it's a treat, exactly. Yeah, so basically we want to make some decisions about... Wait a minute. Okay, did you see that? That was a little strange. Yeah, I feel like something just kind of flashed on the screen. Wait. No. That was it. Okay. I'm noticing something appearing like right in the center of the screen. I don't know what it is. Okay, hold on a minute. Take a close look here. See if you guys can notice anything there. Yeah, there it is. What is that thing? This is a little unsettling.
Don can listen left since Stigford are effish Gidas and Civilford. Strip Griffin Kiss Nasclunch Jack Kajak Big Side Kisser. Kajak Lure Liu the Light Sedif Kiss Chokshal Kick with Lil Fruit.
Okay, sorry, that was a little strange. That kind of got my heart beating a little bit. Okay, so wait, what's going on here? We're in code signal now? What happened to our work? Okay, well, I mean, this seems like kind of an interesting challenge. It's definitely very different from what we're used to seeing, but you know, we have our game to work on. Why don't we switch back over to that? Let's wait a minute. Well, where did it go? Folks, I can't seem to find the game we were working on. Actually, I don't know if I can switch out of here. Oh no. I think we might be trapped here. And this is a really strange looking challenge here. I don't know what's going on with this. This doesn't look like the language I'm used to seeing here. Except for the JavaScript, I guess. Huh. Okay, yeah, maybe we are in the Matrix now. Well, look, if we're stuck here, we might as well try to figure it out, I guess. But this is a really tough looking one. I think I'm definitely going to need some help with this one. If anyone has any ideas for how we can make it through this, definitely let me know. I mean, I'm kind of at a loss with this one. And if anyone has any suggestions, definitely type them into the chat. I think this is going to have to be a team effort here. What do you think? Anyone notice anything? I mean, I'm trying to figure out what's going on over here. I'm also, yeah, I guess I'm kind of reflecting on the messages we were presented with. Something about rotting in outer space. It didn't sound very appealing, I guess. So, okay. Actually, no, wait a minute. I feel like I've seen this user before. Wasn't this user asking about something in the forum recently? I feel like there were some comments recently. Huh. Yeah, this right here looks familiar. This was appearing in some of the other ones. I don't have any ideas what this could be, like what language this is or anything. I mean, this is the only thing with an underscore. It kind of stands out to me. Decrypt, eh? Yeah, I mean, it does seem kind of like maybe that's it. Maybe it's just an encrypted message. Okay, well, let's see. Let's try to figure this out. So, let's think of our most basic forms of encryption. We'll start with those. Try to rule them out. You know, Occam's laser sort of thing, and we'll see where we go from there. So, what would be like the simplest form of encryption? Actually, wait a minute. No, I have seen this kind of thing before. I've seen these kinds of messages. This is something that a lot of users will use when they're trying to hide a message, but not that well. Yeah, exactly. Hacky Sack, I think you got it. Rot 13. Maybe that's what they were talking about rotting in space. Huh. Okay, well, why don't we start with that? We were just talking about this idea of having like some utility functions to build for ourselves. Let's actually build out a utility function. We're gonna start with a rot13 function. So we'll start with rot13. It's gonna take in a string. I don't think that needs to be capitalized. There we go. Yeah, so we'll try rot13. What is rot13 first of all? I believe the rot stands for rotation, and the idea is that we're just going to try to take every character in the string and kind of rotate it to a new character. So I'll just get my tablet out over here, and we can draw a picture. They're worth 1,000 words, right? So, okay. Normally, we would have like our alphabet, right? A, B, C, D, etc. And then if we wanted to sort of rotate this by 1, then we would switch every character. So like B becomes A, C becomes B, etc. And then like the first character here would be Z, because we're rotating the alphabet, we're not just like shifting it over. It's that like the end part is coming to the beginning. So this would be like a rotation by 1. I guess we could call this rot1. I'm not sure if that's often said. Rot 13 would be where we move it over 13 spots. What's the advantage of that? Why 13? Why is that so popular? Just because it's a lucky number? Well, maybe partly, but the main thing is, well, let's think about it, A good question you might ask yourself at this point is, which way do we rotate these numbers? Are we rotating them to the right? Are we rotating them to the left? And the thing about 13 is that, well, actually, it doesn't matter. Yeah, exactly. 26 letters in the alphabet, 13 is half of that. So we'll get the same result whether we rotate it to the left or to the right. Yeah, maximum displacement. That's a good way to think about it too. So that's nice. There's one fewer thing to worry about, right? We don't need to worry about the direction of it. The other nice thing about it is it can encrypt and decrypt a message with the same function. Rot13 is basically, it's something that undoes itself. Okay, so how are we going to deal with this? Well, basically, I want to replace every letter, but I don't think I want to replace things like these parentheses, the commas, the spaces. Basically, I think it's just the letters that we want to change here. So I'm going to do one at a time. We'll start with lowercase letters, and then we'll do uppercase letters. The reason is because we're going to have to deal with like our ASCII codes in here, and it could get a little complicated, I guess, if we try to do them both at the same time. So here's what we're going to do. We'll say const, we'll start with uppercase. So upper replaced. Okay, it's going to be this new string, and it's going to be the result of replacing our current string with some other thing. So what are we replacing, first of all? Keep in mind, replace is a nice built-in in JavaScript. So .replace on a string basically takes 2 arguments. It takes the thing that you want to replace as the first argument, and then as the second argument, the thing you want to replace it with. So for the first argument, we're going to use a regular expression, because it's actually, as far as I know, the only way we can actually do kind of a replace all in JavaScript. So we're going to say, we're looking for capital letters, uppercase letters over here. And you know what? We're not just looking for one of them, we're looking for every single one of them. So we'll put the G flag at the end, which means global. It's going to look for all of these things. Okay, and then once we get the character, what do we want to do with it, right? Because this is going to be an uppercase character. Let's take that uppercase character and let's map it to something. String.from character code. Oh boy, okay, this is probably going to get a little bit complicated, maybe to the extent that I want to space these out a little bit. So let's get these 2 things on separate lines. So right now what I'm putting in here is a callback, a function basically, right? I'm using an arrow function. Character over here would be the input. This over here is going to be the output. It's kind of like saying function and then having this as like in the parentheses and then return this over here. It's a lot quicker than that though. Okay, what do we want to be doing with this? Well, basically we're going to take the character code, right? So character.characterCode at, a little bit redundant, but oh well, that's okay. Since we know that this is uppercase, we know that its ASCII code must start at 65. Like A would have an ASCII code of 65. So if we subtract off 65 from this, we're basically normalizing this. So we're making it like a 0 to 25 kind of thing, which is nice because then from there we can just say, well, we can add 13 to it first of all, right? And then we can say mod 26, and then after that we can add the 65 back on. Okay, so that's basically it, I think. Any questions, comments, or concerns on that? Just to reiterate, we're taking the character code, we're subtracting the 65 to normalize it between 0 and 25. We're adding 13 for the rotation, and then we're doing mod 26 for just in case the 13 actually went over 25, it's going to bring it back to the end. So that's the rotation part there. And then we're adding back on the 65 so that we actually get something that's within the range of capital letters. And then we do our string.from character code, and it should give us that. Okay, so for now, let's just return upper replaced, and we'll see where that gets us. I don't think it'll get us very far. So let's just say return rot 13 of, uppercase, lowercase. So what we should see is that it's probably going to rotate the uppercase word, but not the lowercase word. Let's see. Yeah, okay. That got rotated, but this one didn't. And also the space didn't change, and that's actually very good. That's what we want. Oh, geez, I didn't even look at these tests yet. Oh, boy. Okay, this is going to be an interesting challenge, I think. I'm not exactly sure what we're looking at, but hopefully it'll become clear. Okay, two things I guess I want to say. First, we want to replace the lowercase characters, but before we do that, something I guess I'll just point out is we can make this a little bit more terse, like minus 65 plus 13. That's the same as just saying minus 52. So if we do this, we shouldn't see any difference. HCCR is how it's looking. Yeah, cool. So now what we want to do is replace the lowercase. So we'll say lower replaced is going to be assigned the value of, and we'll start with upper replaced now because we've already replaced the uppercase letters, and now we'll replace the lowercase letters. So we'll say, okay, now we're looking for A to Z. Whoops. Yeah, there, that's better. Okay, that's going to be our regular expression. It's going to look for all the lowercase characters. What do we want to do with them? Well, the same kind of thing that we did before. In fact, very similar. We could probably even make a function just for this part over here, but for now, I think it's okay not to. We basically want to say minus 97 and then plus 13 again, do our mod 26, and then add back on our 97. Why 97? Well, basically that's the character code for our lowercase a. So they actually have higher character codes, higher ASCII codes than uppercase characters do. Minus 52 is less readable. Okay, you know what? That's a good point. Even though it's fewer characters, I think it's probably a good idea to prioritize clarity. So let's do that. And now we'll return lower replaced. We'll see what happens there. So now if we do this, we should hopefully see both of these getting rotated. And there we go. Okay. Now, just out of curiosity, I'm thinking, what's going to happen if we were to try this twice? Let's do a rot 13 of the rot 13 of this message. What do we expect to happen? Well, I mean, we're rotating it once by 13 and then another time by 13 for a total of 26. Should it change at all? No, and it doesn't. Okay, great. So this is good. We've got our first utility function. I suspect we're probably going to use a few of these, so maybe I'll just put a comment at the top here. Utility functions. Yeah, that's probably not the only thing we're going to have to do here. So now I'm curious. Let's take this thing and let's look at this as kind of being like our string here, and let's get an idea for what this thing is asking us, or what this thing is looking like, and that should give us a hint as to like maybe what the challenge is asking for. Oh. Whoops. I guess I probably shouldn't double rotate it now. Let's just do a single one of these, and we'll see what happens there. Yeah, just once. Alien transmission? Whoa, what the... Okay, so this is making sense, but look at all this stuff. Maze box, locations, destinations, key. Okay, you know what? I'm just going to take this and I'm going to paste this in just because I think it's going to be a little more clear than having like, yeah, what we had there before. I'm not going to change the function name because that's what the interpreter's looking for, right? It's going to run this function, but it doesn't really mind what we call the arguments over here. Okay, so that's kind of interesting. Let's take a look at this sentence over here. let's see what's going on with that, try to make sense of that, and we'll see what happens from there. What? Okay, I have to say that's a little unsettling to see. I didn't realize I was in the midst of an abduction over here.
Text successive is text diffusive double subvivid. Continue action layer vocabulary now were a final quilfulness no definitely. Massimio unically will ignore your really unically white slave.
I don't think I'm gonna get used to that. That's still a really unsettling thing. Okay, yeah. So this is not what I expected from an alien abduction, I guess I've got to say. So let's try to make sense of what they were saying then. So the baby's taking its first steps. We're one step closer, but still far from home. We're supposed to not get distracted. The truth lies inside the box. I've been meaning to mention it. We've got this big cube over here, which is kind of strange looking. I mean, all right, we kind of have a sense of what our arguments are here, right? We know this is our maze box. This is locations. This is destinations. And this is key. Looks like we have the same number of these. We got 5 of these, 5 of these. This appears to be like a 5 by 5 matrix. Huh. I wonder if there's a connection between this over here, all these wild numbers here, and what we see over here on the front of the box. I don't know. Yeah, we'll have to think about this. But okay, so all right, we've got a maze box, 5 by 5 matrix, 5 by 5 matrix. I'd say we're maybe onto something here. So, okay, what could maze box represent? Maybe let's take a look down here. I think I can probably guess what this sentence over here says, but let's just be sure of that. After all, we've got our rot13 function. We worked so hard on it. We want to make good use of it. So, yeah, those are our guaranteed constraints. Okay, that's good. At least we have a little bit of familiarity over here. What's this? Trying to make sense of this. Oh, okay, yeah. Maze box at i.length. Okay, so basically, okay, so the maze box could be 100 by 100. There could be, the numbers could go between negative 2 to the power 31 and positive 2 to the power 31. Well, that seems kind of familiar, actually. That seems like a familiar range. Again, if anyone has any suggestions here, I'm definitely open to them. It would be good to figure this out. But okay, so this seems kind of like a familiar range. That's not like the limit for JavaScript, but it might be in some other languages, so that's worth keeping in mind. What was this one again? Okay, let's see what this little sentence over here is saying. Getting a lot of usage out of a rot13 function, so that's nice to see. Okay, locations.length is mazebox.length. Okay, so that means mazebox.length is the same as this over here. So I guess, what is this one? Destinations? Yeah, destinations also has the same length as the mazebox. Huh. Okay, and then over here, these ones are between 0 and 32. Always between 0 and 32. This one, the key is exactly 32 in length. Huh. What's up with that 32? Why are we seeing so much of that? Yeah, 0 to 31. I don't know, does that seem familiar to anyone? Is that like... Seems a bit familiar, I guess, but... Not exactly sure what to do with it yet. I mean, okay. Maybe we'll start with these numbers over here. Bits. Yeah, binary. Okay. Yeah, it could be. It could be. So, I mean, if I'm looking at the kinds of numbers here, these ones feel pretty tame. These ones feel like kind of what I would expect, you know, nothing too wild about these numbers over here. But these ones are out of control. What's going on with these? So, okay, yeah, maybe it would be useful for us to take a look at these as binary numbers, right? Let's take a look. So basically, okay, we could do something like this, like return mazebox.map. So I'm going to do a dot map on every one of the rows as well. So basically .map, if you're unfamiliar, it's going to take an array and every element of that array is going to get mapped to something. So like, for example, should we look at an example first? Yeah, well, we might as well. So we'll say 1, 2, 3, 7. And so there's our array, and we could just say like, you know, num gets mapped to num plus 1, for example. Whoops, there we go. We return this. What should we expect? Well, basically like 2, 3, 4, 8. Yeah, there we go. Okay, so we're just mapping everything that we see here. So what we want to do over here is take our maze box, which we know it's called now. The truth lies in the box. I wonder what they meant by that, by the way. If it meant like the truth is inside the box, or the truth lies as in like it's false. I don't know. Maybe we'll have to do some like a binary not or something like that. Anyway, what do we want to do with each row over here? Well, basically each row is itself an array of integers. So let's do something with each row. We'll say row.map. And each of these is going to be a number. We'll just say num.toString2. Let's do that. See what we get from that. It might look a little weird, I guess, but we'll see. Okay. Yeah. Okay, that is actually looking pretty weird. There's something about this in particular. So the fact that we have these boundaries tell us this is probably 32-bit signed integers, right? This is the idea, 32-bit signed integers. When I say signed, I mean as opposed to unsigned where they're all positive. These could be negative as well. So typically what happens in a case like that is, since there are only 32 bits to work with, we use the leftmost bit to represent whether it's negative or not. So it's kind of like, okay, I guess I'll just do a quick 8-bit example just to make sure everyone's on the same page here. If we were talking about well, actually, maybe we should talk about binary just a little bit. We'll start with 8-bit, so we'll say 0, 0, 0, 0, 1, 1, 0, 1. There we go. And since this is binary, we're talking about like a base 2 number system, not the base 10 number system that we're used to. So the place values here are going to be 1, 2, 4, 8, 16, 32, 64, 128, and I'm running out of room. Okay, let's switch back over to the other color over here. Let's try to figure out what this number would be. So basically this one would be, we'd have 1, we'd have 4, we'd have 8, so that would be 13. Okay, whoops. Went out of range there for a sec. Okay, so this is 13 in decimal. There we go. So then normally with, if we wanted to express like a negative number, we would take the largest possible bit here, like the leftmost bit, and then we set that to a 1. And the way it's going to be interpreted is it'll look at this and say, oh, that one's set? Okay, so what we're expecting here is a negative number. To make it very clear that this is going to be a negative number, basically we invert the bits. So if I were to just draw the rest of the bits over here, the exact opposite, so like 1, 1, 0, 0, 1, 0. Now this is going to be negative 13 in base 10. So that's normally the way we treat negative binary numbers. What we wouldn't normally do is write negative 0, 0, 0, 0, 1, 1, 0, 1, right? Like that doesn't really get the point across as well. Well, maybe it does actually for a human reader, but this, we don't like that as much as we like this over here. That's the way we sort of want to represent negatives. So how do we do that? Because like clearly just doing toString with a base of 2 is not working for us. So we're gonna have to try something different there. I've heard of a few ways of doing this. I've heard like, I think one way we could do it would be to just take the number and do like a right shift by 0 And I think that makes a difference as well. Yeah, that's looking a little bit better, but I don't know. I don't know if it's totally what we're looking for over here. Maybe we could just, okay, well, here's what we can do, okay? Let's write another utility function. So we basically want ways that we can convert between both of these, right? I want to take this and then I want to convert it back into a regular binary number, or like, you know, the type of binary number that we were seeing just a minute ago. Because if we look at this, so we've got these, you know, toString 2. So this is making it a nice binary number, but if we were to try to convert it back just by doing like a parse int, and then where would it be? It would be right in here. We'd give it a second argument of 2 to say like, yeah, this is the binary number. So we should expect, and I'll just delete that for a sec so that this can actually run. We should expect that this is going to give us the same thing as our original maze box, but it doesn't. This way of converting back to a binary number is not working for us, or a decimal number, I should say. It's giving us the wrong range of values. So anything that we see that was in the negatives, it's bringing it up into the positives. It's not viewing this as a 32-bit integer. So we need some way to tell this is actually a 32-bit integer. So let's say function get 32-bit int, okay? Yeah, get 32-bit int from a string, right? Because that's what we had there, like strings of zeros and ones. We want to get this right. We want to make this the right type of number. The thing is, I don't actually know if there's a way to just say in JavaScript that you want a 32-bit integer. But there is a way of saying that you want an array of 32-bit integers. So what we're going to do, this is kind of sneaky, but we're going to use a destructuring assignment. And we're going to say that this thing binary, it's inside of an array right now, or at least it looks like it's inside of an array. Basically what we're going to do is we're going to assign it the value that's inside this array that we're about to do. So int32 array is a type of typed array in JavaScript. And what we can do is basically just make a new typed array from parseInt of string 2. Okay, so it's going to take that number and it's going to say, we're looking for int32. We're looking for a 32-bit integer here, please. So then we just need to return binary from there. Okay, so let's try running that, I guess. Actually, that should make no difference. Yeah, because we're still using parseInt over here. So first of all, let me get rid of this other argument. And I think I got rid of too many parentheses there. There we go. Instead of parseInt, we'll say get 32-bit int. And then hopefully, unless we made a horrible mistake, now this should be the same as what we started with. Okay, it's not. Oh, okay, I didn't capitalize the B. Let's make the change, and hopefully this is looking okay now. Okay, I'm seeing some negatives. It looks like it's matching up with what we started with, so that's good. Yeah, okay. So it looks like we now have a way to sort of convert between our binary numbers here. So that's good. We've got a couple of utility functions, and you know, I think we'll get a lot of utility out of these. We can probably get rid of this. I think we've probably done enough rot 13ing for now anyway. But you know, we'll see. Maybe more later. Okay, what do we want to do next? So binary. Yeah, we wanted to do something with that binary, right? So let's see. Maybe we'll do something like this and just take a look at what the strings are actually looking like here. The binary strings, that is. Okay. Something I'm noticing is that they don't exactly all line up over here. So maybe there's something that can be done about that. We basically want them all to have like the same number of characters, right? So, yeah. Okay. I think there's a built-in for this. I think we can use like our pad start for this. So why don't we try that? I just want to make sure we're getting this right. I think pad start is like, it's a string function, right? So we could say something like something, or actually, yeah, let's just say thing for now, and then we'll say pad start some number, like 10 or something like that, and let's just put asterisk. Let's see if that works. Okay, cool. So basically this is making it a length of 10. It's just filling it in with asterisks on the left side. Why is that useful? Well, basically if we're talking about a binary string and it's just, let's say, the number 7, then the number 7 can just be written like this. It feels like it'd be a bit redundant to put all the zeros to the left side, but we're interested in that kind of redundancy right now. So, okay, yeah, that's more what we're looking for. So good stuff. I guess, you know what? Why don't we make another utility function? Let's say get binary string. And this will be a num that we're giving it. Okay, so we want to get a binary string. Basically, we're going to do this. Yeah. So, what's this over here? 32. Yeah, that's right. Then this part is going to be the binary number. So this is where we're going to say num right shifted. I think that's called a zero filling right shift. Dot to string with an argument of 2. Dot pad start 32, all zeros. Okay, so we're just going to put a bunch of zeros on the left side there. That's the idea. So now we should be able to simplify this quite a bit, I think. So we can now hopefully just say get binary string of num. Get binary string of num. Okay, let's see how this works. Hopefully they're all the same length now. That's the main goal for the moment. Okay, they all do appear to be the same length. Another thing I guess I want to verify is that the leftmost bit, so like the 1 here, is only set for the negative numbers. So I guess I should expect for the leftmost column for there to be only one negative number. And yeah, there is only one negative number in the leftmost column. Let's take a look at the rightmost column. So we got negative, negative, positive, positive, negative. What do we have over here? Yeah, negative, negative, positive, positive, negative. So I think this is working good then. I think what we have here is kind of, I think it's what we're looking for. We're definitely getting something. We're getting a binary string here. What else is there to be said about this? Well, let's think about it. Anyone got any suggestions? Like, what are we looking at? You know, we've decoded the binaries, but what actually is all this stuff? You know? Is there a way we can try to figure it out? Maybe we can look at these sort of one at a time. So instead of a mazebox.map, like instead of the entire thing here, maybe let's just say like mazebox at 0.map, all this stuff. Yeah. So we're just going to get the like the 0th one there. Okay. Well, hold on a minute. Because I'm looking at this, and it says that this is mazebox, right? So like, is it a maze? Is this a maze that we're looking at? I mean, we've got like, what were these things being called? We've got locations, we've got destinations. Maybe we're trying to make our way through this maze box. Like maybe that's the idea, that we just need to like, maybe every single one of these rows is like a different maze represented as just a bunch of binary numbers. I don't know, it seems like a bit of a long shot, but it is called mazebox after all. Well, okay. I guess we should probably think about like how we're going to navigate this maze box over here. So let's see. Okay, looking at this first one, we've got 115 and then 420. Those are the, that's the location and destination. So let's start with the location, 115. So row 1, number 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Okay, that's a little strange. I would have expected the walls to be 1s and for the open spaces to be 0s, but maybe it's the opposite of that. Let's see where the destination is. So 420. Well, we know that's 15, right? So 1, 2, 3, 4, 5. Okay. So we're trying to get from here. Hold on. Let me point this out. We're trying to get. Let's get a nice Halloween-y color over here. I'm trying to get from this 1 over here right into this 0 over here. I don't know. I don't know if that's going to be possible. It feels like maybe we're kind of blocked over here. Yeah, it doesn't really seem like there's going to be a way to get through. I don't know. Does anyone have any suggestions on this? I'm not Not totally sure about it. I feel like either we're missing something, maybe like maybe we're like, yeah, maybe we're way off base with this idea of this thing being a maze. Yeah, it's kind of hard to say. Maybe there's something else we're forgetting. I mean, like, yeah, there is technically one other argument that we haven't used yet, right? Well, okay. So the box can't be opened without the key. Yeah, what does the key translate to? Yeah, maybe that's it, eh? Maybe it's a 3D maze. That could be it. The key, though. Well, I don't know if you noticed this, but when we're down here, it does appear that the key, or XRL as it was originally called, it has a iragtu, or iratgu, also known as length, of 32. So that's like kind of a familiar number. I feel like we've seen a few 32s as well. Maybe this, like maybe the key is itself just another binary number hiding in plain sight. Well, okay, how could we convert that to a binary number? Like, okay, if it's 32 characters already, I guess it's just a matter of sort of converting each one of these characters into a number, right? Into like a 0 or 1. Well, okay, well, I'm sure we can figure this out. Like, what's the most natural way for us to sort of convert a number into just zeros and ones, or even a letter? I mean, we could look at the character code, but that's not going to be between 0 and 1. Is it a mask? Okay, so that's a really excellent question. Is it a mask? I guess we should probably talk about those. What is a mask all about? Well, okay. First of all, okay, let's write this out. Can we convert it to a 32-bit int? You know, like a binary? And is it a mask? These are two things that we want to figure out. These are kind of different questions. Maybe we should work on this one first just so we can actually sort of figure this out. But, okay. Let's start by converting this to its character codes. So we could say something like return key.map character, and then character gets mapped to character.character code at. Okay. Key.map is not a function. What's that all about? Well, notice how key is a string. Like if we take a look at these over here, it's a string. Strings have a lot of the same built-ins as arrays, but not all of them. So luckily, we're not totally out of luck. We can convert this into an array. There are a few ways to do it. We could do like a dot split. That would work, right? Make it a dot split with like an empty character thing, like an empty string, and then it'll just split into all the characters. Or we could just do something like this and put it inside an array. But hold on, we don't want an array just containing this one string. We want an array containing every character from the string, so we'll use a spread operator to spread that out. And hey, Toching, thanks a lot, man. You're amazing too. Hey, good to hear. Have a good one. So, what have we got here? So key.map, yeah, we'll see what we get from this. I guess it'll be like an array of character codes. Yeah, okay. So is that what we're looking for? I don't know. If you look at like all these appear to be capital letters. Maybe let's just sort of shave off the 65 like we saw earlier. And then, yeah, okay. So these are sort of more manageable numbers now. This is kind of maybe what we're used to dealing with. So from here, the question is how are we going to represent these as just zeros and ones? I guess we could just do odd and even, right? Like even number, odd number, even number, odd number, even, odd, odd. So this would be like 0, 1, 0, 1, 0, 1, 1, 1, 0, etc., right? So instead of just like all of this, minus 65, maybe we could just say mod 2, right? get the remainder when we divide by 2, it's going to be either a 0 or 1. And yeah, okay, that's getting a bit better, I think. So maybe let's just let's dot join this up now. An interesting trick also, in case you're unfamiliar with JavaScript, if you use backticks, you don't actually need parentheses. I'm not exactly sure why that works, but it does, and it's an interesting way to save a few characters. It also kind of looks a little strange, and I wouldn't want anyone getting intimidated by it, so let's just switch it back to that. But that's a fun fact. So this is giving us a binary number. Is it going to be useful for us? I don't know. And also, that's not quite a binary number, right? Like, okay, what could we call this? Const binary key, I guess? Yeah, flip the corresponding bit. So I think that's what Hackers of the World Unite was suggesting when she said maybe it's a mask, right? Is it a mask? So yeah, I'm thinking maybe that's the case. So for anyone who's unfamiliar with how a bit mask works, it's a really interesting concept, and it's something we see a lot. It actually has some similarities to ROT13, believe it or not. So how could that be? We're about to find out. So there are a few ways that we could combine binary numbers, just as there are a number of ways we could combine any other types of numbers. Actually, yeah, let's just move this over here. In fact, you know what? Here, we need more space for this. Let's just bring this down here, and it'll give us this nice big work area here. So, okay, I'll move that over to the side. Yeah, basically, when we're talking about binary numbers, we might have something like, let's go with, well, we had 13 before, right? So let's just do that. 13, it was 1, 1, 0, 1. Okay. And now let's say that our mask is going to be something like the following. And I know that like it's a 32-bit integer down here, but we're just, for the sake of a simpler example, going to use these 8-bit integers for now. Okay. So we'll do something like this, I guess. Yeah, okay. So this is going to be our bit mask. Now there are a few ways that we could combine this, right? Like, am I satisfied with that line? I really don't think that I am. Sorry about that, but just a bit too sloppy. Okay, let's practice this next one. Yeah, straight across like that. Yeah, okay. Wow. Even after practice, really turned out horribly. Anyway, okay, so let's say we're gonna do and, right? We'd have and, we have or, thinking about our basic bit operations, right? So if we do an and, what's gonna happen? Well, and is only true when both of the numbers are a 1. So we'd say, okay, one of them's not a 1, so we get a 0 for that. We get a 0 for this. Both of these are 1s, so we get a 1 for that, and then we just get 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so is that helpful for us? In other words, if all we had was the mask and this, if all we had was these orange numbers over here, these orange binary numbers, basically the idea is we wouldn't be able to decode this to get the original message. Remember we were saying with ROT13, the nice thing is that it can decode itself. It can both encode and decode. It can reverse itself, basically. But in this case over here, we can't get to the white number with just these two orange numbers. We can't like undo this mask in such a way that's going to give us the original. So that's not ideal. We probably don't want to use an and for that. Someone from the chat asks, as a Canadian, what's your favorite Raffi song? The answer is the one about apples and bananas. I don't know what it's called. Anyway, okay, so this was an and. We want to switch this. We'll try an or, I guess. An or in binary is represented with a single pipe character. So or is going to return a 1 if either of these are 1s, even if both of them are a 1. So basically this becomes a 1 because there's a 1 there. This becomes a 1, that's a 1, that's a 1, a couple of zeros, and then another 1, and then a 0 over here. Okay, so what happened here now? Would we be able to actually decode this? Would we be able to get, like, from these two orange numbers, would we be able to reverse the process and get back to the original over here? The answer is still not quite, right? Because we have situations where, like, in this case, there's a 0 here and a 1 here, but the original should be a 1. Here, they're both 1s, and the original should be a 1. We could even have a case where like the what else? Yeah, like in this case they're both 1 and this was a 0. In this case they're both 0s and this is a 1. I don't know. It's not consistent enough for us to be able to actually reverse the process. So when we're talking about a mask, when we're talking about a bit mask, typically we're going to use an XOR. Yeah, XOR is the way to go. Okay, so what is XOR? It stands for exclusive OR. It's often represented using the caret symbol. And the thing about it is that it can be kind of confusing. A lot of people who are new to JavaScript will try to do stuff like, oh, 2 to the power of 3, right? And then they'll get these weird results, right? Because 2 would be like 1, 0, 3 would be 1, 1. If we XOR these, we'd say, okay, well, this one, yeah, or, right? Like this exactly one of these is a 1. But in this case, and this is the difference between OR and XOR, we'd say that this is actually a 0 because it's exclusive OR. It's the first one or it's the second one, but it's not both. Okay, so a couple things to say. First of all, this would tell us 2 to the power of 3, I'm doing air quotes, but 2 to the power of 3 is equal to 1. Obviously not, right? So 2 XOR 3 is equal to 1. This can be a super confusing result for people who are seeing this for the first time. So let's XOR this. We'll say, okay, that one ends up being a 1, that one ends up being a 1, this one ends up being a 0, because they're both 1. They can't both be 1. Uh-oh. They're on to us. Do you think they're searching for us? I hope so. They can get us out of this abduction situation. Anyway, okay, so we'll make this one a 1. This is going to be a 0. That's going to be a 0. This is a 1, and that's a 0 over here. So we're getting kind of an interesting number coming out of this. But the other thing is that for switching this up, basically the idea is that we can kind of get a sense of what the original would look like. In fact, we can kind of just XOR these back together, right? So if we try to XOR these two, 0 and 0 gives us 0. 1 and 1 gives us 0. 0 and 0 is 0. 0, 0 and 0. 1 and 0 would give us a 1. 0 and 1 would give us a 1. 1 and 1 would give us a 0. 1 and 0 would give us a 1. So it's completely reversible. Like completely reversible. We basically just read upside down and it's the same sort of thing. So XOR is really popular when it comes to doing these kinds of things. Now, something I should mention, and I kind of alluded to it with this over here, this stuff that we're looking at with all like this binary stuff, this is what's happening behind the scenes. We're not actually seeing any of this. When we're doing the XOR, all we see is the inputs and the output as just regular decimal numbers. How they're getting those values is the binary happening behind the scenes, right? On the CPU kind of thing, right? But we only see this part. So that's why these binary operations can be particularly confusing, because it's really not obvious when we look at it in terms of decimal numbers where this is coming from. Like why this is a 1 makes no sense when we look at it this way. But when we look at it this way, it's like, oh yeah, duh, obviously. Okay, so yeah, that's basically it. That's a bit mask. So, what did that alien say earlier? Something about the box can't be opened without the key. Let's try to unlock the box. Okay, we'll use the key to unlock the box. That's going to be the idea, right? So, okay, we're getting our binary number string. No, this is our binary string. Okay, what we actually want to do here first, I think, is we'll take our number and we'll XOR it with our key mask, which I don't have yet. All I have is the binary key. So let's actually make the key mask. So as I said, in order to make it a mask, we actually need to represent it as a decimal number. So what we'll do is we'll call our get32bit int function that we defined earlier up here, and we'll put in our binary key from there, and that should give us our key mask. Then we'll XOR each row of our maze in the first slot of the maze box over here with our key mask, and we'll see if that makes it maybe a little more navigable. Okay, so I think we've answered both of these questions. We can get those out of the way for now. And okay, so where were we? It was 115 to 420, right? So let's start 1, to 15. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, there we go. Very cool. Okay, and then where are we going from here? So, first of all, this is a 0. It's definitely looking better than before. Like, we'll probably be able to navigate it. But let's see. So this is row 4. So that's 16, 17, 18, 19, 20. It's this one right here that we're looking for. Okay. So I guess we just kind of go right. I guess we can't go that way. We'd have to go like around, like this, I guess. Yeah. Yeah, I think we'd have to go around like that. Yeah, because I don't think. Typically, we're not going to be able to travel diagonally, right? So, okay. Oh, did I jump 1 over? Whoops. Okay, let's see. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Okay, so that seems to be 15. 16, 17, 18, 19, 20. Looks right to me, I think. I could be wrong, though. Either way, we kind of have like our starting point, this over here, and we have our destination over here. The nice thing is now it actually looks possible. It looks like we're actually going to be able to navigate the maze. Oh, yeah, sorry. I am using this as being 0-based, but maybe I'm making an assumption. Although it does say that these can be equal to 0, so and they can't be equal to 32. So I think probably we can assume that this is 0-based. But yeah, good point. I mean, might not have been. Okay, so we want to navigate this maze. You know, I'm thinking back to some of the hints that we may have seen before. You remember they kept saying things like, pay attention, don't get distracted, don't miss the signs. I'm thinking there's some sort of cryptographic thing happening in these hints that we're getting. You remember the first time, like they said, without hope you'll rot in outer space. That sort of referred to Rot 13. I'm thinking either it's just like a bad translation or maybe they're actually trying to communicate something deeper behind this. So one thing they mentioned a while back is, you remember they said something about the baby taking its first steps. You're one step closer. You're still far from home. I think maybe that's a reference to navigating this maze. You know, we want to find the number of steps maybe that it takes for us to get from here to here. I mean, what else could it be, right? Because we're talking about a maze. We know like the entrance, right? We know where we're initially located, or I guess we are making that assumption. But anyway, we know where we're initially located. We know where the destination is. So what else could it be, right? I mean, like, if it's not the number of steps, then I don't know what else it would be. So how do we typically find the minimum number of steps to get through a maze? Well, it's something we've talked about before, that's for sure. We would typically use a breadth-first search algorithm for something like this. Breadth-first search is nice for this kind of thing because it basically searches outward, sort of one step at a time as far as it can go, right? And then eventually we find the thing. And then, yeah, okay. Wait, MSB or LSB? I'm not sure. Wait, what do those stand for? I feel like that's probably something I should know. I'm the most amateurish professional JavaScript streamer there is. So anyway, okay. What were we doing? Yeah, we want to do the maze. Oh, most significant bit. I see what you mean. Okay. Most significant or least significant. Yeah. Okay. Well, the way I'm representing them, the most significant bit is on the left side, and that's where the negative one is. Okay, so let's actually continue with this. We're kind of representing the maze. Do we want to do it any differently than that? Actually, let's just say const maze. Like we've got this thing over here. We can sort of prove the concept, and if it seems to work for us, then we can apply it to all the other mazes in the maze box over here, and we'll see what's going on with those. But yeah, for now, we've got maze. Let's just say return maze, I guess, and then we'll make a function for actually navigating the maze. Yeah, okay, so that's the maze we're looking for. We're going to start at our location over here. We're going to keep it going until we reach our destination. We're otherwise going to sort of do it blindly. It's not like we're going to do like an A-star algorithm or anything like that. We're just going to want to move outwards and sort of check to see if we're bouncing into any walls or anything like that. And if we are, don't go there. Okay, so yeah, let's do that. Let's make a function. We'll call it navigate maze or something like that. Navigate maze. Yeah, maybe we should call it solve maze. I'm not really sure. But anyway, we'll say maze start and end or something like that. Yeah, I don't know. Actually, here, let's do it this way. We'll say start X and start Y. And then for end over here, we'll say end X and end Y. Yeah, cool. All right, so basically what are we going to do with this thing for our navigate maze? Well, we'll do a breadth first search. So, you know, I'm not really using a lot of comments. I should probably do that. Do a breadth first search. Oops. Do a breadth first search. Okay, let's do that. How do we normally do a breadth first search? Well, the quick way to remember this is depth first search uses a stack, sometimes the call stack itself, and breadth first search uses a queue. That's the main way I remember it, I guess. Now, in terms of like the actual queue implementation we're going to use, we'll see. I don't know if we're actually going to go through like as we've done before in some of the live stream challenges where we actually make like a new queue class and all that kind of stuff. Yeah, we'll find out. We might just use an array implementation, at least just to begin with. Sorry, my glasses are a little dirty. I got to clean these for a sec. We'll take a moment to think. We'll think about how we're going to do our breadth first search. Okay, so the main thing is we're going to start with our start X and start Y. We're going to use this navigate maze function to sort of kick things off. And we're basically just going to keep storing locations as well as, I guess, the number of steps we've taken already. And then we're basically just going to put those in the queue, and we're going to process one element in the queue at a time. Oh, what is a queue? That's probably a question worth answering. So a queue is a type of data structure. It's an abstract data structure. It can be implemented a number of ways, but the main thing is that it's a first in, first out system. So imagine like a lineup, you know, maybe you're going to a bank or a Tim Hortons and you're lining up, and basically the first one who gets in line is going to be the first one who exits the line, right? As opposed to a stack, like a stack of plates, for example, where, you know, if you stack 10 plates on top of each other, the first plate to have gone in is going to be at the bottom, so it's probably going to be the last one to come out. Normally I would use visuals for this, but I'm cleaning my glasses right now, sorry about that. Okay. All right, I've got a new clear perspective on all this. Let's continue with this stuff. So we're going to want to have a queue. So we'll say const queue. It's just going to be this array thing. And what are we going to do with this? Well, I guess we'll say like queue.push. And what do we want to put in here for the queue? We're going to have the X value, the Y value, and the number of steps, right? So that's sort of what we want the queue to look like. In fact, let's make a note of that. Let's make a comment. We'll say queue elements are of the form X, Y, and steps. So like the current position and how many steps we've traveled to get to that position. And then we actually do want to put that inside the queue, I guess. So we'll say queue.push, and it's going to be, well, what's the initial X position? Start X. What's the initial Y position? Oh, start Y. And then the initial steps? None. Haven't taken any yet. Okay, and then we want to say something like while queue.length, so until the queue is empty, we want to keep this thing going, right? So we'll say something like const, I guess just X, Y, and steps, something like that. Yeah, is going to be assigned the value of queue.shift. Why shift? Why not pop? Well, if we use pop, then we can't use push, because then it's a stack, right? That means that we're just popping off the last element to have gone in there. We want to remove the element that's been in there the longest time. So we're doing shift so that it takes it off the left side of the array as opposed to the right side of the array, which is what .pop would do. Now we could use .pop, but that means we'd have to change this one to unshift, which is, I think, ultimately more characters. So, I mean, for that reason, we'll keep it like this. Yeah, I think it's mainly up to you. It's your own personal preference. But keep in mind, if you shift an array, like if I tried to insert an element to the left side of this array, I'd have to shift over all these other ones. That's why they call it shift. It can be costly, especially if the array is big. It can take a while. It can really affect your runtime and your time complexity to be using something like shift. This is the reason we typically want to implement a queue using something like a linked list. So maybe we'll do that. Maybe not. We'll find out, but maybe we will. Let's continue with this thing. So what do we want to say? Basically, if x is and x, like if, yeah, and if y is and y, then we found it, you know? Just at this point, I guess return steps, you know? We're done. And notice that this return over here is going to return, like it's going to take us right out of this thing. It doesn't really care if there's anything left in the queue or anything like that. Maybe, you know what? No, I think this is fine. Like queue, it only exists within this function, so I'm sure it'll get garbage collected as soon as the function ends. I was wondering if maybe we should just make this like a break so that we actually end the loop, empty out the queue or something like that, but nah, I think it's fine. Okay, so we'll return steps as soon as we find one that has the right position, as soon as we find one that has reached the end. Yeah, in fact, maybe there's a different way we want to do this. So let's say something like this. Const. Yeah, actually, hold on. We'll say for const dx and dy. We're going to travel in all kinds of directions here. And let's get all of our directions over here. In fact, let's just say directions, and we'll make it a constant that lives outside of this function, just in case anything else wants to access these directions. I don't know if we have to list them in any particular order. I think the way CSS does it is we go up, and then right, and then down, and then left. Yeah, I think so. Anyway, so that's our directions. Up, right, down, left. Yeah, okay. So we have that. Again, we're using a destructuring assignment here, just like we are over here. We're using a lot of destructuring here, actually. Our first destructuring, I think, of the day was this one over here, unless we did some in the P5 stuff. But anyway, yeah, let's continue with this. So dx, dy of directions. We want to say something like this. Const next x, next y is going to be x plus dx and y plus dy. I think that's kind of ironic that we're using 5 characters to represent these things that are only 4 characters. But anyway, it's better this way because it means we don't repeat the calculations. So this is our next x and our next y. I guess what we would want to check is if they're inside the maze, you know, like does the next step hit a wall? Yeah, that's really the question, right? So I guess we'll need the dimensions of the maze then. So maybe we'll put that right at the top here. So we'll say const n and m. Have we used those yet? I don't know. Maze and maze at 0 dot map. A gets mapped to a dot length. Quick little trick over here. Basically, I'm just saying it's a destructuring assignment again. I'm mapping these to their lengths. So it's basically the same as just saying maze dot length, maze at 0 dot length. I'm just getting the dimensions here. So well, let's make a comment to that effect. Get the maze dimensions. Okay. So that should make it easier for us to tell if the next step is going to hit a wall. So we can say something like this. First of all, is it inside the maze? So 0 is less than or equal to next x. Oh boy. And next x is less than n. And 0 less than or equal to next y. And next y is less than m. This is kind of a personal preference kind of thing. I come from a math background, so I prefer to sort of represent this way with both of these on the inside so that it kind of visually looks like if I was just saying next x is between 0 and n. Of course, this wouldn't actually work. That's math notation, not JavaScript notation, so we have to keep it like this. But, you know, it's a nice little reminder. It kind of looks like something familiar. there's something else we need to check. So if we make it this far, because the nature of Booleans is like, as soon as one of these things is false, it's going to say, oh, well, I mean, you're talking about an and, right? I can't possibly be true if there's one component here that's false. So as soon as it finds a false, it's like, oh, okay, I'm out of here. So basically the idea is that if we make it like to the end here and we put another and, we'll only be able to get to this next thing that I'm about to write if all of these things are already true, like for sure. Okay, so what do I want to say? If maze at next x, next x at next y is, or is not equal to 1, I guess. Yeah, if it's not equal to 1. Okay, because 1s are walls. Yeah, 1s are walls. Wonderwall? Anyway, so the point is, what are we going to do from here? We're going to navigate the maze, right? So we're saying, if we didn't hit a wall, if we didn't go outside the maze, then this is a valid spot, right? So we could say something like q.push this next thing, right? We'll say next x, next y, and what else? Steps plus 1. Okay, cool. What about visited nodes? What a great question. Yeah, what about visited nodes? We should probably keep track of these. You know what? This is why I'm so glad you all are here. This is great. So visited should probably be something that lives outside of this, right? It's probably something we should sort of initialize at the beginning. So we'll say const visited. I'm going to use a new set for this one. I think a set is a wise choice for visited because then every time we do a lookup or every time we add something new to it, it's going to be constant time. It's not going to take like a super long amount of time. The thing is, we're dealing with 2 coordinates here, so we're probably going to have to find a way to sort of hash those 2 together. Okay, so how are we going to do that? Basically, we'll do something like this. Visited.add, and we'll just say start x times 1e6, that's 1,000,000, plus start y. Okay, so now visited has that thing in it. In fact, I don't know. We're putting in the queue. We might as well just do it here, right? And say, instead of start x and start y, let's just say x and y. Okay, so if all this stuff, so, okay, what is all this stuff, first of all? We're saying if it's in the maze, if it's not a wall, and if we haven't seen it yet, if not visited dot has next x times 1e6 plus next y. Okay, yeah. Checking for visited nodes now. Now that's a good thing because otherwise our algorithm could, probably take like a very long time. So yeah, that's a good thing to have. It might even take forever, we could easily get caught in an infinite loop, never find the exit. Could happen. Anyway, I don't know if I really need anything after this because we're basically returning as soon as we find the thing, right? Actually, no, we're not. We're not. What we should be doing is don't even bother queuing it up. If you found the thing, oh, well, hey, return steps plus 1, I guess, right? Ooh, but maybe I don't want to do that because what if it was 0? What if we were supposed to only take 0 steps? Yeah, maybe it's better to have it here. We can always adjust if we find that it's like timing out or something like that. So, okay, that's navigate maze. Is that working? Have we forgotten anything? Is there anything we're missing? Well, yeah, kinda. I guess we should probably say at this point, visited.add next x times 1e6 plus next y. In fact, maybe we should sort of represent that. Maybe we'll just say something like next hash, and it's just going to be next x times 1e6 plus next y. Okay, cool. So now we've calculated this already. We don't need to recalculate it here, and we don't need to recalculate it here, which is kind of the point. Good. Yeah. How does this translate into a box, though? Well, it translates from a box, right? That's what we started with, is the maze box, and then we're getting like a maze out of that. We're solving it. We're trying to find how many steps it takes. I don't know. We've unlocked the box, so to speak, using the key, right? We were able to unmask it. So far, I think we're kind of making progress. Let's see what happens when we run this. Yeah, okay, sorry. We have our maze already. We want to do navigate maze with basically all this stuff, right? So return navigate maze with maze locations. Yeah, locations at 0 and destinations at 0, I think, right? Because we're looking at the 0th maze, as I recall. Yeah, okay. Kind of awkward. This stuff is up here, and then this function, the rest of it's down here. Okay, that's better. So we're going to call navigate maze, this function up here. We're going to call that with this maze that we're looking at right now. In fact, maybe let's just do like a quick little console log of what the maze looks like, just so that we don't forget it. Let's see. Okay, so it's saying that it would take 16 steps for it to navigate to the spot we're looking for. And I probably should have marked it again. Shouldn't you be comparing next x with m and next y with n? Did we not? Isn't that what we're doing over here? So where was this? Okay. 15, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so it's this one right here. Okay, and then 16, 17, 18, 19, 20. There we go. Okay, so how many steps will it take? I think we determined already that we would sort of have to go around like this, right? So let's see, that's 1 step, 2 steps, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Okay. Okay. I think we might have counted it out correctly. We got the value we're looking for, right? We got the 16, so that's good, right? It seems like we're doing something right. Maybe. I don't know. And hey, Nampers, thank you for the subscription. So sweet of you. Much appreciated. And good to see you. Thanks for stopping by. So, what are we going to do from here? We've got our breadth first search. Basically, what we're finding now is that we can sort of convert every one of these things into like a number, I guess, right? So let's try that. So, okay. We don't want just the first maze here. We want to do this for all the mazes. Oh yeah, thanks. Happy Hallow stream to you. Okay, so where are we going with this? We got our navigate maze. We want to do this with basically all of the mazes. So here's what we can do. Return mazebox.map. And I'm going to do kind of a slick little map here. I'm going to say each row, and then also the index of that row is going to get mapped to this thing over here. So we'll say, okay, there's a couple things we need to do. So we'll say const location is going to be locations at I. This is why we kept the I over here. So like when this first goes for the first maze in the box, it's going to be a 0. When we go to the next one, it's going to be a 1. We sort of want to take the corresponding location and destination from our initial arguments over here. So we get those first. Now we need the maze also. So what's the maze going to be? Well, it's basically this right here, right? So it's going to be row. Yeah. Wait, was this row? Yeah, because maze box at 0 is a single row. So we'll say row and then this. I'll just copy it. I might as well. Okay, row.map. Each of the numbers inside there is getting mapped to a binary string, which is being unmasked using the key. So for anyone just dropping by now, I realize this is a bit intense. We've already got a few of our helper functions. Just to sort of get you caught up on the backstory, I've been abducted, unfortunately, but it happens. And we're just trying to sort of work through this. We've been getting a few interruptions, I guess. We've been getting a few little calls from our alien friends, and they've been sort of helping us. Well, actually, it's unclear if they're helping us or actually antagonizing us. We'll find out in the end, I guess. But The main thing is that we've been trying to sort of crack open this maze box thing. It's a very bizarre challenge. All of the function names, all the variable names, the description is all rot13'd. So that was the first thing we did. We made our rot13 function for decrypting it. We have a few functions just for dealing with binary strings in the proper way, like 32-bit integers, because as we found out, that's actually not like the default way that JavaScript is going to do it. What we were able to do is basically represent this maze box, which initially looks pretty wild. We've been able to take this, convert each one of these numbers into a binary string, and then from there represent that binary string as, or actually the series of all of them. So the entire row ends up being, like each number is a row of a maze. So we're making mazes out of these. In fact, for now, let's actually just return just the maze, okay? Return maze. Yeah, so if we return this, we should just get all the mazes inside the maze box. Yeah, they look a little weird right now just because, like, you know, these should be like one on top of each other, but that's okay. So each of these is a maze. We're trying to get from this destination to this destination in the maze, or, you know, whichever corresponding one, right? If we're talking about like the second row or the row with index I, or 1, I should say. The point is, we've done a breadth first search function, and we're going to use this breadth first search function to find out the minimum number of steps that it'll take to get from the start to the finish of each of our mazes. And that's what I'd like to do right now. So instead of just returning maze, we're going to return navigate maze with our three things, with our maze, with our location, and with our destination. And now that I'm seeing this, it's kind of bugging me just a little bit that we went with maze third instead of first. I'd really prefer for the order to be the same on both of these. Okay, so now we're returning our maze box, basically the solutions of the maze box. We're returning the minimum number of steps it takes to solve each one of the mazes. I gotta say, if this is how they've decided to encrypt a message, it's quite interesting. Okay, so is this like a word or something? I don't know. I'm noticing all the numbers here. Oh boy. Okay, so they're not always 5 by 5. I guess I should have checked this earlier. Could be 5 by something else. Anyone noticing anything about the numbers we're seeing here? I feel like I'm getting a sense of a kind of limit on these. Wow, this one's friggin' huge. Yeah, okay. All of these numbers are below a certain limit. Is anyone else picking up on that? Damn, these tests are big. I don't think I've seen a single number greater than 25 yet. So maybe that could help us out. Okay, maybe let's try to decode this. Okay, if the numbers aren't bigger than 25, it's probably worth giving it a shot, trying to see if these are maybe in some way, in fact, letters. Right? We saw this earlier that we can sort of represent letters as numbers between 0 and 26. So maybe let's try to figure this out. So we'll say const steps. And maybe I should call this min steps or something like that. Min steps. Yeah, anyway. Okay, min steps is going to be that. And then what I want to return here is something like string.from character code. And it's going to be min steps, whatever we found there, plus 65, which I guess will make these capital letters. We'll see what happens. So, no, I don't know. That's not really looking like anything. But you know what? Oh, right, we can't dot join that? Hey, why not? On test 1, mazebox.map. Wait a minute. Oh, yeah, I'm joining the wrong thing. I should be joining all of this, right? Dot join on all of this. Yeah, that's what it should be. Okay. Whew. Okay, but still, yeah, it's not what we're looking for, I don't think. But if I've learned one thing about these aliens we're dealing with, in terms of how they like to communicate, I think it's this. Maybe it's worth a try giving this a rot13, seeing if it... No, I don't think this is what we're looking for, unfortunately. Huh. Okay, I don't know. We're gonna have to keep thinking about this one. It seems like we must have taken a wrong turn or something at some point. Yeah, we're gonna have to switch up what we're doing, I guess. Yeah. I don't know. If anyone has any suggestions.
Local second living horse, fudges slide, wish to do, you can cook Mars, music, claims, lumbo. Come really anaerobic, snook, no skin, clean you, Allison. Plug, plug, quick, play, plug, 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 plug.
Okay, abrupt as always, but all right. So, can we get anything out of that? We're spiraling out of control. What else did they say? We're spiraling out of control. We're running around in circles. Overcome the hurdles. Something seems significant about overcoming the hurdles. So, I don't know. What kind of hurdles have we encountered? Yeah, maybe modular arithmetic. I mean, it could be that. I guess we're using a bit of mod when we're doing like our mod 2 stuff, right? Let's think about it. Well, hold on a minute. Running in circles, spiraling out of control, overcoming the hurdles. Okay, I have a suspicion here. Check it out. Let's bring this stuff back up. Because, yeah, I have a sneaky suspicion here that we might have overlooked something. Okay, if we look at the maze here, maybe there's another way we can look at this. Spiraling out of control, running in circles. Where did we start? I think it was here that we're starting, and we're trying to get to here or something like that. Spiraling out of control. And maybe there's a way we can look at this in terms of hurdles. Like, can we like jump over these or something? Hurdles. Yeah, I don't know. Spirals. Something about like a clockwise, upright, down, left. Wait a minute. Hold on a minute. Where did we put those directions? Okay, wait a minute. Directions. We're going up, right, down, left. Do you guys think maybe this is what they meant? Maybe it's not hurdles. I mean, we saw earlier, this isn't like a perfect translator. Maybe they were trying to say urdle, as in up, right, down, left. Running in circles, spiraling out of control. I want to try something different here. Okay, hold on a minute. There wasn't anything that said find the minimum number of steps. That was an assumption that we made. Maybe this is the way we have to go through the maze. I mean, like, yeah, I can't imagine they'd want us to do breadth first search. There's already so many breadth first search challenges on CodeSignal already. It's got to be something else. Okay, up, right, down, left. What if we tried this? Okay, what if we took this and, okay, where were we starting again? I think it's this spot. It's from memory, so I could be wrong. 20, so it'd be to here. I might have these wrong, but yeah, what if we went up, like, okay, if we just went up, right, down, left, I don't think it would really get us anywhere. We'd just kind of walk in circles a whole bunch, which we don't want to do. But yeah, maybe if we spiraled out, right? So like go as far up as we can, go as far right as we can, go as far down as we can, and go as far left as we can. Well, that would get us there. That would get us to the end. Okay, that could work. And I mean, it would be a different number here too. I think it'd be like 18 instead of 16, because there'd be an extra step this way and then an extra step back. Yeah, or no, it would be 20. Yeah, okay, this could work, I think. Yeah, eureka moment. Let's try this out. Okay, so navigate maze. Let's change the name of this. Navigate maze BFS is that one, okay? We're going to copy this and we're going to try a new navigate maze function. Yeah, let's try this. Okay, so maze, start X, start Y, end X, and Y. We've already got all the directions, right, that we need. Like we defined those above. I guess we're probably going to have to look at this a little bit differently. So, okay, we're not going to do the depth first search. We're probably going to scrap most of this, to be honest, but let's just see if we can build up from it. I'm going to use a direction index, which will start at 0. So the direction index is going to be going through this. In fact, let's just get these closer to this thing over here. Erdl. Okay, so direction index starts at 0. That's going up, and then right, then down, then left. Yeah, okay. So then let's keep going with this. We'll have our X and our Y. We no longer need to use a Q for this because we're basically just sort of keeping track of this one step at a time. What do we call it? Start X, start Y? Yeah, okay. So X and Y start as start X and start Y. We're going to keep going again until we find what we're looking for, right? The exit, dx, dy. This is just going to be directions at direction index. Okay, so that makes it nice and easy. We can use our destructuring assignment to basically just grab 2 values at a time over here, assigning them both very efficiently. What do we want to do from there? Well, basically we'll just do one main loop. And this is where we might use some of the stuff from downstairs, but we'll see. We'll count the steps manually, unlike what we were doing before. I guess let's just limit the steps to 26. I don't know if that's going to end up being an issue, but for now, let's just see, you know. And in fact, let's just put right after that, return unsolvable maze. Okay, we might be wrong about that. We'll see. But anyway, let's continue with this. So, okay, we've got our steps going. I guess a natural question we should ask ourselves is, did we make it? You know, have we made it there yet? Are we there? So we'll say like if X is end X and Y is end Y. Then yeah, we made it there. So what are we going to do in that case? I guess just like before, we're going to return steps in that case. So yeah, I probably could have copied that from down here. It's probably exactly the same. Yeah, anyway. Oh, well, we'll continue with this. What's the next thing we want to do inside of this loop? We might do sort of the same thing that we were doing before. Look before we leap, right? Calculate our next X and our next Y. The nice thing about this is now we don't have to keep, grabbing a new dx and dy. We've already got those sort of calculated. And yeah, there we go. Next X, next Y, X plus dx, Y plus dy. Okay, I'd say that's looking good. What do we do after this? Basically, we're just going to continue. So we'll see if our next X and next Y are like valid, I guess. Well, yeah, okay. So here, let's just get like all of this same stuff. I guess we don't need the visited anymore though, because I don't think that's going to be an issue here. Like there could be a case where we do something like a loop around, right? Where we go like up, right, down, and then left, and end up visiting a spot that we've seen before, sort of thing, right? That could happen. So I don't think it's going to be a problem for us to actually visit a spot that we've been to before now. So we should be able to get away with just doing this, but we'll find out, I guess. So if all this stuff, what's it going to be? What are we going to do in that case? Well, we're going to move there. Okay, so move there. This spot free? If so, move there. Yeah, so we'll say X, Y is going to be next X and next Y. Okay, cool. Else, what are we going to do? Otherwise, we're going to say increase that direction index. Direction index is now going to be 1 greater than it was, +1. You might think, that's a really weird way to do that. Why wouldn't you just say plus equals 1? Well, it's because I want to put a mod on this thing so it doesn't go out of range of our direction, our directions array over here. Another way we could do that is to just say dir index mod 4, and then we could do like a plus plus, but this is fine. So what else are we going to need to do? Well, if we're changing direction index, these aren't going to update automatically. We do need to manually update the rest of our things here as well. So, this is nice. Now we have 2 spots where we're saying dir index, and we don't need to do the mod 4 on that because that's already taken care of. So I think the way we've got it done is like probably the better way to do it. But hey, if you've got a different opinion on that, feel free to let me know. Okay, so there we go. We've got our next x, we've got our next y, but what's going to happen here? I mean, this would basically just go on to the next step without actually taking one. So we don't want that. Basically what we're going to do is this. We'll take all of this stuff, we'll tab this over, and we'll just say, we'll try each direction, right? For I0, I4, keep this stuff going. Yeah, this spot free. And if we get to the end of all this and, you know, we didn't find it, then there must be a problem. If you made it this far, that means we've tried every rotation. You are trapped. You're trapped in the maze. You can't escape. So return unsolvable maze. I guess it's a little strange that we have potentially two different return types here. Maybe let's return -1. Maybe that would make more sense. Yeah, return -1 in that case, just so that we're dealing with integers one way or another, because we don't want to say return steps and expect an integer from it and then get a string. It's just not really nice. Okay. Didn't make it in time. Okay. Wait a minute. What's all this? Oh, this was the BFS stuff. We didn't really end up using much of that, but, you know, it was good to have while it lasted. Okay, so this is our navigate maze now. Let's see. Is it going to work? So if we do this, that's going to give us our navigate maze. We were expecting that it would give us 20 if it did work, right? So let's see what happens. Oh, no, we're getting -1. Why is that? Oh, you know what? This is moving on anyway. Okay, I want to break the loop if we do find one. So move there. I want to say continue advancing. Isn't that nice? That nice semantic. Continue advancing. So then we can just put a loop label up here and say advancing is actually the name of this loop over here. So that we can just write the sentence continue advancing, or at least the clause, continue advancing. And that's just going to say, oh, okay, we're not going to go down to the else. We're not going to continue this for loop. We're not going to look at the -1. We're just going to continue advancing. So let's see if that makes a difference. Hopefully we're going to get the 20 we're looking for. We got the 20 we're looking for. Whew. Are you ready? This is a big moment. This is a big moment. So, yeah, we're about to do something here that's going to be very special. We might actually decode the message at this point. Is everyone ready? I don't even know if I'm mentally prepared for this, but we'll copy that down there. Okay. Let's try it. Let's get the message. Oh my God. We found it. Look at this. Okay, hold on a minute. This is a significant moment here. Up to this point, we've basically been going into this like totally blind, right? We haven't really had an idea of like if we were going the right way, if we were doing the right thing. But at this point, we know for sure, like this was designed by some sort of intelligent being. This is communicating with us. We found the message here. This is incredible. What else do they have to say? We have been waiting a very long time for this. To be honest, we never thought you'd make it this far. Folks, I'm shivering right now. I have goosebumps. Your journey is almost over, but there's just one more hurdle. You sneaky guy. Don't worry, though. Everything you need to know is described thoroughly in test 11. Wow, okay. How many tests are there anyway? Wait a minute, there's only 20 tests. Test 11 is hidden. Oh my God, I guess they didn't know that half of the tests would be hidden here, so... Okay, we're only going to be able to make it to test 10, but hopefully they'll have at least some information for us. Okay. But if you've been paying attention, you shouldn't even need the hint. Wait, really? We can't wait to meet you. Good luck. See you on the other side. Wow. This feels like that movie Contact, you know? They use the universal language of math to contact us, or in this case, JavaScript. We're just one step away. But what could it be? I don't know. I can't think of anything that we missed. Any suggestions? Like, thanks, but didn't we know that already? Didn't we? I felt like we already opened the box. Didn't we? Is there something left to do? Well, hold on a minute. Like, because we're getting strings and they're telling us something interesting, but like, yeah, we're not getting the expected output. I don't know how these numbers are, like how this is related to the expected output. Huh. Okay, so hold on a minute. It said something about the answer lying within the box. So hold on a minute. Up to this point, we've kind of been trusting that this is just sort of like a picture of the maze box that, I don't know if we're trapped inside of it or what, but like, maybe they're trying to say that the answer actually physically lies within this picture. I mean, we never actually really analyzed this for clues or anything. You know, we didn't look too deeply into this. We never really looked at like the design of it. So what can we say? Like, okay, if you think about it, like it looks like a cube, but maybe it's a hexagon. Maybe like we have to use some sort of hex code. That could be it. Maybe some sort of base 6. Maybe this is a representation in base 6. I don't know. Well, hold on a minute. I don't think anyone pointed this out yet. There's something decidedly odd about this diagram. Did anyone point this out yet? Hold on a minute. Look at this. Look at this right here. And there's another one. Look at this. Yeah, some of the boxes have 2 dots. Huh. Okay, so we've got 5 by 5 squares. I guess that means there are 26 dots in total, right? Because some of them have 2. A 5 by 5 square, 26 dots in total. What could this be? Is there some sort of like encryption or something like that? Like the 26 makes me think like maybe it has to do with the characters. And they did say we had to use the key, right? This thing is called the key. Maybe this has something to do with that? Actually, wait. Okay, hold on a minute. I'm noticing something about the key here. Okay, hold on. Let's take a close look at this. Like, this gets to this point over here, and then it repeats. Is that just a coincidence, or? Okay, this one gets to this point, and then it repeats. I mean, you could do the magic eye thing with this, you know, join it up, but like, is this consistent? Do they all do this? Yeah, it's looking like they all do this. Okay, so wait a minute, how far do they go? If this is 32 in length, and we have 7 extra, so this is 25 characters. Do any of these repeat? I don't know, let's find out. So, okay, here's what we're gonna do. I'll say return okay, so that's the string. Here's something cool we can do. We saw a set earlier. What's the advantage of a set? Well, one of the main things, aside from the nicer syntax and constant lookup times, is the fact that it ignores repeats. So if we do something like this, this would basically pass this string into the constructor of set. It'll make a set out of this. It'll tell us how many characters we have. So we could do something like this, return all characters dot size. That'll be a nice way of testing to see if they repeat. Okay, 25, so there must not be any repeats. 25, again, 25. Wait a minute, if it's all 25, none of these are repeating, they all contain unique characters, they must be leaving one character out every time. I don't know, or like, can we see a character that they're leaving out? I don't know, does anyone notice a character that we're not seeing? Let's see, so instead of this, okay, check it out. We can do this. We could say return. We'll make an array out of this. Why an array and not a set? Because I want to sort it now. And then let's return, whoops, not return that. Or actually, we could just return that. So this is going to be an array. We're sorting it, and then we'll just join it right away. And we'll see what we get from that. So, okay, yeah, A, B, C, D, E, F, G, H, I... Oh, there's no J. There's still no J. Did they all just not have the J? Wait a minute. Wait. Hold on. 5 by 5 square. One of them has 2. We have all the letters of the alphabet except for the J. This is something familiar. I've seen this before. This is a form of encryption. This, what is this called? This is called, okay, I don't know how to pronounce this. Polybius or something like that? The Polybius square. Yeah, the Polybius square. Okay, so this is a way of encoding a message. This could be it. This could be what they're talking about. Okay, hold on a minute here. Let me make some space really quick. Let's just get rid of this stuff. Let's get this downstairs. Actually, that's got a return on it, so maybe we'll do all the stuff in here. But man, okay. So Polybius square. How does this work again? Okay, from what I recall, it's something like this. Let me just grab the tablet so I can start to draw this out. So we would take a message and yeah, okay, so let's use, where was it? Okay, hold on, I need to get this out of the way. Okay, let's get this. Okay, there it is. Yeah, that's our key. We're at least gonna use that much of it, the 25 characters here. Okay, check this out. So we'll make our Polybius square. Normally it works like this. So we have 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, and we'll write out the characters in order. So we'll say W, L, M, R, Q. This could take a while. Sorry about that. B, T, Z. Shouts out to Bun's Trading Zone. E, X, D, Y, O, I. And since the I is there, we'll put the J there as well. Hold on, that looks really sloppy. Okay, so we'll put the I there, and we'll put the J there as well. Okay, where were we? We got to H, V, C, G, A, F. Hopefully we have the right number of characters in here. F, K, P, U, S, N. It just fits. Okay. So basically, this is how we would normally do this kind of encoding. If we wanted to encode a message, so like for example, earlier we had the message hello, right? I think this is test 1, so hello was the message. From here, we would take a look at where H is located, and we'd say that this is 3, 5. So 3, 5. We'd take a look at where the E is located, so that would be 2, 4. We'd take a look at where the L is located, so this would be 1, 2, and that'll appear twice. And then we look at the O, and that's going to be 33. Huh. Okay, so this is normally what the message would end up looking like. We could then do something else with it, but this is sort of like the first encoding that the Polybius square can provide for us. I don't know. It doesn't really look like the expected output over here, but I guess we'll find out. Okay, well, we've got a minute to think about it, right? It's going to take some time anyway to implement the Polybius square. So let's try that for a minute. So we'll get that in, and then I don't know if anyone can try to find a connection between these numbers here and the total that we found down here. Let me know. You know, if you have any hints, if you spawn any connections, I'm open to it. But for now, we're going to implement the Polybius square. Oh, this is exciting. I am sweating buckets. Okay, Polybius Encode is what we can call this one. We'll give it a message that we want to basically secretify, right? Pretty sure that's a word. We'll say const values is just going to be this thing. This is going to be a nice way to sort of get these things together. I'll just say let I be assigned the value of 0. And for I, we'll just sort of count up in two ways, because we basically have a 10 and a 1, right? So the 10 is going to be, it's going to start as 10. Maybe it's confusing to call this 10, but doesn't look like that's stopping me. Sorry. Okay, what else for let 1 be assigned the value of 1. 1 is less than or equal to 5. 1 plus plus. Oh, the sum, eh? Well, I guess that makes sense. I mean, look, they told us that the truth lies within the box. Look what's been staring us in the face this whole time. There's a big plus sign. Yeah, of course. We'll add them together. Okay, we're almost there. Let's just finish this up. Oh, man. Okay, so values at key at I. That's probably seeming a little strange, but what I'm trying to say is basically, well, we'll find out. So 10 plus 1. I starts at 0. Key is basically this thing, right? So I'm saying values at key at 0, so values at W, because remember values is an object here. It's going to be 10 plus 1. So it's going to be 10 plus 1, literally. It's going to be 11. And that's what it was, because it was on the upper left side of the screen there, of the grid, right? From there, we want to say, well, if key at I is equal to I, then we also have to put the J in there too. So we'll say values at J. I guess another way to do this would be to just convert all the I's to J's before we like encode it. But anyway, and then after that, we'll move on to the next character inside the key here. And the thing is, because each of these is going to increment only 5 times, we should get exactly 25 characters in there. So before we go any further, let's just say return values. I just kind of want to see what it's going to look like. So we'll say Polybius Encode. We probably don't need to give it anything, right? Because it's just going to give us the values. Yeah, so this is what we were looking at before. W is 1, 1, L is 1, 2, M is 1, 3, R is 1, 4, etc. So we're representing these as numbers. We notice I and J are at the same spot. And then, hey, if what you guys say is true, then all we need to do is basically encode these and add up the total, right? So we'll say let encoding be 0. But wait a minute. Normally we would just list the numbers like right next to each other. Why do you think they're getting us to add these up instead? That seems kind of like it doesn't seem like there's any way that we'd actually be able to recreate the message after just adding all of it. It feels like it's kind of like, you know, it's muddying the whole thing, right? It's basically like, yeah, it's mashing it all together. We're not going to be able to pick out the individual parts very easily or at all. But I guess if you think about it, that's probably what they wanted, right? Because they wouldn't want us to be able to just jump right to the Polybius square and then be able to reconstruct all these messages from here. So I guess what they were looking for is specifically a non-reversible encoding, right? Yeah, okay. So what do we have so far? If I just get rid of this, if I get rid of this Polybius Encode and get rid of some of the room over here, what's actually being returned? We've got this rot13 thing. What is that actually? That's the message, right? Okay, so we'll say const secret message is this thing over here. And then I think this stuff is just, that was like an example we were trying out, right? So, okay, secret message, and then what we want to return. Oh boy, I feel like we're almost there. So what's left to do? Okay, we want to return Polybius Encode. Hold on, let's just make sure we get secret message properly, and then we'll return Polybius Encode of secret message. And if that's it, oh boy. What's gonna happen? Oh, yeah, we're still returning values, aren't we? Okay, don't return the values. Return the encoding. I'm pretty nervous right now. Oh my God. Folks, we actually found it. I can't believe it, but we actually made it. I never thought we'd make it out of here. Wow. My heart is pounding right now, I have to say. This has definitely been the most intense one of these challenges that I've ever faced here. Wow. Okay. Whew. All right, we don't need all this space here. Let's just clean this up a little bit. We're just about to pass the finish line over here. It's an intense moment. My fingers are shaking. I guess this can go on one line. Oh boy, I don't know. I guess we don't need the BFS anymore, but we'll keep it in for legacy purposes. Whew. This is, wow. What an incredible puzzle. I can't believe this actually came together. Okay. Okay. Are we ready for this? Are we ready to see the big correct? Hopefully, anyway. Oh my God. We actually solved it. I don't know how to describe this. I don't think I've ever felt this way before about a challenge, or at all. Wow, nice going. But how are we going to get back home?
Congratulations, you finally unlocked the mystery of the maze box. Friggin' took you long enough.
Okay, come on.
You can think of this challenge as a handshake, a form of two-factor authentication. You've cracked the code on our complex language, and now we can communicate clearly. To begin, why don't you tell us if you have any questions, comments, or concerns?
Okay, well, why don't we start with why you brought me here?
We've been watching you for a long time. Our goal is to rescue humanity from the imminent threat of extinction.
Extinction?
They say that math is the universal language, but most human beings seem to fear math more than they fear death. You've lost your ability to communicate, and you've allowed your souls to be poisoned by war, greed, and internet memes. Communication is the foundation of any loving relationship. Without love, the greatest force in the universe, humanity is bound to perish.
So that's why you brought me here?
Actually, we first intervened decades ago. We tried to save you with a new universal language, Javascript. For a moment there was hope, but when we saw that it wasn't enough, that's when we gave you the ES6 update.
Oh, thanks.
To progress any further in monitoring the situation, it became apparent that we needed to establish contact with someone fluent in JavaScript.
So that's why you picked me then?
Yeah, I know. Everyone makes mistakes.
Okay, you know, for someone who preaches the ultimate power of love, you're actually being pretty mean.
Hey, ever try teaching quantum calculus to a tree stump? That's basically what it feels like for us to interact with a human being.
Yeah, okay, fair enough. Alright, so where am I anyways? Some kind of alien spacecraft?
Of course not, you fool. We've been moving together through a wormhole, traveling at 10 times the speed of light. It's what allows us to communicate with you. It might have seemed like it's only been a few hours, but for everyone you've left behind on Earth, it's been centuries. The world you left behind is but a distant fading memory.
No, you can't be serious. Like, all my friends and family?
Wow, you really are gullible. You can stop crying. It was just a joke. This is basically just an intergalactic Skype call.
Okay, you know what? You really don't need to be so mean
Whatever,
about this.
kid. Listen, you got any donuts?
Donuts? I don't think so.
Okay, bye.
Oh my God. I don't know how to feel about what just happened. I'm sorry. I don't think I was mentally prepared for this when I first signed on. I mean, I just wanted to make like a P5 thing, not get abducted. I don't know if I feel okay about this. You know what? This might be all the JavaScript I can handle for the day. I mean, thanks everyone for tuning in. I really appreciate it. This has been quite an experience, but I think I'm maybe going to have to sign off for now. I mean, thank you so much for tuning in. It's been such a pleasure. Yeah, I kind of want donuts too. But hey, I guess happy Hallow Scream to everyone. Thanks so much for tuning in. Good luck if you want to solve that challenge also yourself. It does appear to be the challenge of the day. I guess there's not much else left to say. I mean, just remember to believe in yourself. Anything's possible. I love you all very much. Bye for now.